Alexander. I don't have the last test with me right now. Can you just plug them into KimSketch and check the names? I guess I can try and look it up. I don't even know which exam I posted for you guys. What year does it say on it? Let's see. 2018. Cancel. Come on, little buddy. Apparently my new computer needs a PDF reader on it. Come on, Twinkie. Come on. I activated my Word on here yesterday. Now it's telling me it's not activated. Okay, so the first one would be, let's see, R stereochemistry. So 2R butan 2-one. The second one would be cycloheptanone. And the third one would be 1, 2, 3, 4, 5, 6, 7. So the bromo, let's see, 1, 2, 2S, 2-bromo, 6-methyl, 7, so heptanal. Yeah. Come on, Twinkie. Come on, you're driving me crazy. Come on. Come on. Oh my goodness. What is going on? Sorry, you guys are going to have to deal with me here for a second because I think the problem is I just hadn't opened up Word since I downloaded it yesterday. Okay. Okay. The first one, come on. It was it was butan 2-all. I think it was R stereochemistry. Sorry, my computer's having problems. So I was hoping this wouldn't happen. Yeah, butan 2-all. That's right. And I think it was R stereochem, right? Also, I'll write this down. There's I don't know, maybe 25 or so. That's right. Except you added buntan instead of butan. But yes, you got it right, Alexander. Yeah, that's right. If you want to be technical, then the R can go in italics, but kind of not necessary. All right. So my computer might be doing something weird here. If for some reason this shuts off or something, I will get back on as soon as I can. Just give me a few minutes. Apparently it's still trying to upload and do stuff with my new Microsoft Office. So other questions? Okay. I think we're in the clear on weird stuff. So, Alexis, the only way we have seen cis-trans stereochemistry is in ring structures. So you need a constitutional isomer, which is the same formula but different connectivity, like what we learned last exam. I don't remember the exact formula, but if I had something like this, and oh, wait a second, let me make sure that I have the right window up. I do not have the right window up, so you can't see what I'm doing. Okay, so if I have something like this, that's what, 1, 2, 3, 4, C5, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, O, right? So I would need to do a constitutional isomer with cis-trans stereochemistry. So I could do something like a cyclobutane with a methyl and an oxygen on it. So that would have cis-trans isomerism. One of them could be cis and one could be trans, right? So that's all in understanding what those words mean, right? So constitutional means completely different connectivity than what you started with. So it's not talking about stereoisomers. But it's saying find a constitutional isomer, so something with the same formula that has cis-trans isomers, which means it has to have a ring. We will learn where alkenes can also have cis-trans isomers, but we haven't done that yet. So hopefully that makes sense. Let me know if I need to clarify that further. Onyx has been kind of needy ever since I got back into town, so she's kind of laying on me right now. So if you hear her smacking her gums, just forgive a very old dog. Hi, Tony. No problem. Here to help. More questions? You guys are quiet tonight. I don't believe you're this quiet tonight. Can you give me a more specific question over what you don't understand about the different types of strains? Like ring strain is from the angles being not 109.5 when they need to be, and it happens in rings. So actually, I will defer to your book on that one for the examples, because there's a lot of examples in your book of that, and they're much prettier than what I'd be able to show you on here, because they actually show all the bond angles involved. But if you have, cyclobutane, this bond angle here, there we go, is about 90 degrees. That's not what it should be, right? It should be 109.5 because it's a sp3 hybridized carbon. So that creates bond strain or angle strain or ring strain. I usually call it ring strain. I think your book calls it, what do they call it? Angle strain? Yeah. If you are talking about, if you're talking about steric strain, that's where you have groups running into each other. So for example, make sure you guys can see that okay. So if I have a butane molecule, right, this has 3 hydrogens right there. That has 3 hydrogens right there. These hydrogens right there are very close to each other. That creates steric strain. A less strained version or conformer of that would look like this, because those hydrogens now are very far apart and they're not able to interact with each other. So that is steric strain. You get this with the 1,3 diaxial interactions. You get it when you have things that are syn-periplanar, or when they're basically laying on top of each other like that. And then if you are looking at something with torsional strain, that one's a little bit harder to kind of visualize. It looks a lot like what you would expect for torsional strain, except the molecules aren't, or the atoms aren't really big enough to actually interact with each other, but they still seem to repel each other. And we think that's because of interactions between the non-bonding orbitals. So if you think about something like ethane, just something real simple like that, and we looked at Newman projections for this, right? So this was the lowest energy conformation, and we called that one staggered, right? And then we had the eclipsed form, where these groups are essentially laying on top of each other. And even though they're not big enough to interact with each other the same way they can on the butane example, we do think that their orbitals overlap. So that's essentially torsional strain, is overlapping non-bonding orbitals. Steric strain is kind of things, electron clouds kind of bumping into each other and kind of repelling. And ring strain is just a strain from rings that don't have the appropriate bond angles because of the shape of the ring. Hopefully that makes sense. Karis wanted to ask how to do the 4 isomers again. Well, there's about 40 different ways to do that. So it's kind of however you do well with it. So for me, I usually start with kind of a generic structure. Give me a second. There we go. And then you need to put in there we go. You can either look at them and have them kind of to the side like this. You can have them rotated straight up and down. That's kind of how I've been doing it in class, I think. Like that. Sometimes, and some people prefer to have them kind of flat, like left to right sort of, instead of straight up and down. So it's kind of however you want to do it. And then let me give you one that actually has some stereochemistry here. So I'll go ahead and put one with the hydrogens behind. So, you know, if you're looking at this, you know, if I give you a molecule and say draw the 4 isomers, draw one of them and then draw the other 4. And so figure out what this one is. Look at that stereocenter and label it. Look at that stereocenter and then label that one. To do the enantiomer, it's easiest just to draw the mirror image, right? So if I am wanting to do my mirror image, I would need, let's see, oh, I need carbons. Sorry, this is kind of slow going. Onyx, that was really gross. Okay. So, let's see. And my CL would be back there. I'll be honest, I was trying to avoid doing one of these tonight because they take so long to draw out on a computer screen. Okay, so now I have the 2 isomers, one of which is you know, one isomer, the other one is the enantiomer of that. So what you can do is then go through and kind of look at that area that I just highlighted and draw it on this one here. That would give you the other isomer. That would give you, you know, if you had RR and SS, it would give you RS, and then you can do the same thing. Or you can flip 2 groups. That gives you the other isomer. So if you wanted the other isomer here, you can move the hydrogen here and the OH there. That would give you the other chiral center on that one. So again, there's a lot of ways you can do that one. Let's see, Fisher projections. Can you quickly show how to count the number of flips? Okay, Caitlin, I need you to try and rephrase that question because what you wrote doesn't make any sense. When we're talking about flipping a molecule, we're talking about cyclohexane chair conformations, but your question doesn't seem to indicate anything like that, and any S versus R. So I'm not exactly sure what you're asking me. So submit again, ask me again. Following these topics, can you demonstrate putting a chair conformation into a Newman structure? I can do that. Let's see. And again, this is in your book. You guys have lots of problems in your book that has this. So, I love you too, Jasmine. But let's see. Oh, Jasmine, I'm completely sorry. Drawing enantiomer and diastereomer molecules. Well, I mean, that was like 5 days worth of lecture, so I can't really go over that. If you have a specific question, then yes, I can. Just ask me a specific question, though. but like demonstrate putting a chair conformation into a Newman structure. So let me do a chair conformation. Oh, that got kind of ugly. Let me try that again. It's still not perfect, but I can do better. I swear I can do better. Okay. So usually when you're looking at a Newman projection of a chair conformation, you're going to, I usually look at it like whatever's on the left-hand side, those are the ones that I'm going to look down. If I want you to look down something else, I'd have to tell you as well. But if you're just trying to kind of generally do a Newman projection, I'm going to draw my little booby looking guys there. And then let me highlight that. So this one here and that one there are going to be the ones in the front of your chair conformation or of your Newman projection. Then the ones behind here are going to be these. Okay. So if you notice, this one there in purple is pointing down, right? Between the first two that I have burgundy highlighted. So that one's going to be pointing down, right? So I'm just going to go ahead and fill in the rest of the front two. And then in the back, let me do that. Then in the back, I can fill those in. And then you'll notice in the very back, this one there is the one pointing up. So it should look like that. Okay. Now, if you have something on this molecule, so let's say back here in the, whoa, that didn't look good. There we go. I have a bromine in the equatorial position pointing up, right? So everyone has one pointing up and one pointing down. So I'll put a chlorine there. So I need to look on that side of the molecule, which would be this one here. Okay. And so the one pointing up is a bromine, right? Because this thing there is pointing in the up direction on that carbon. And this one down here would be the chlorine. Okay. If I have something on, let's see, let's do something there. Okay, that one's in the axial position pointing straight up. Well, I can put it in the axial position pointing straight up. If I don't have anything else, then I fill them all in with hydrogens. I won't give you any where you have a substituent at those two positions because you wouldn't really use a Newman projection for anything like that. Okay, so hopefully the color coding helps on that one. Can I draw constitutional isomers in perspective that show cis-trans stereochemistry? I did that at the beginning of this video, so when I'm done, go back and watch it. Other questions? Double check my email. Hopefully what I'm talking about's making sense. Let me make, ask me if something's not making sense. Other questions? My Twinkie's laying underneath my computer. It's adorable. Do I need to like sing you a song? Can I get confirmation you can at least hear me? Sometimes when I don't see anybody asking questions, it makes me assume that you guys aren't hearing me or seeing me. Okay, good, you hear me. I don't think I know how to count the number of flips in a Fisher projection and find its stereochemistry to find S or R. Well, you don't use a... Oh, for some reason I was thinking Newman projections. I think you asked for Fisher projection earlier and I got confused. I'm sorry, because somebody else was asking about Newman projections. Let me blow that up so I can see your question. Number of flips in a Fisher projection to find its stereochemistry to find if it's S or R. Worked a few and did not get the same answer as you in class. So, okay. No, I'm sorry, Caitlin. I think you actually asked me that earlier. Okay. Yeah, I totally was like adding two of the questions that were asked together and I got confused. I'm really sorry. Your question makes perfect sense. It was me, not you. Okay, so let me pull this one back up because it is a pain in the butt to do Fisher projections on the drawing program. Okay, so let's just kind of take a molecule. Let's just do something really simple. Okay, let's do a hydrogen back there, a bromine there, an NH2 group, and then we'll leave the other as a methyl. So I can convert that to a Newman projection, okay? If I look at the stereochemistry on this, bromine would be number 1, the nitrogen would be number 2, and the methyl would be number 3. So I can look at that and already tell that it's our stereochemistry, right? Well, let's look at something, let's kind of look at that in a converted way. So if you're looking at a Newman projection, the big wedged lines are coming out at you, and the dashed lines are going behind, okay? And it doesn't matter how many chiral centers you have, it's lined up that way, where everything's coming out at you like wings almost, and then the others are going behind, up and down. So if I try and rotate this, I'm going to do it so the NH2 kind of comes up over here. The hydrogen would be right there. The bromine would be on top. And the CH3 would be down there. Okay. That might be hard for you to do without a model kit. So if you are like, how did she do that? Well, use a model kit and rotate it until you see what I just did. So what I have here is the kind of format that I have to use to make a Fisher projection. Okay, so I've got my bromine on top, I've got my hydrogen on the side, I've got my amine on the left, and my methyl group at the bottom. So if I'm looking at this, I can tell that it does not look like the kind of standard I have in my mind of 1, 2, 3, 4, right? So that's what I'm trying to make it look like. What I have is 1, 2, 3, 4. Okay, all I did was just took the same numbers I did over here, right, to determine R or S, and just applied those down here and just wrote them on top of where I would normally put those groups instead. So I need to flip my 1 and 2 because those are not where they need to be, okay? I'm trying to get to that one up there, right? So if I flip my 1 and 2, I have 1, 2, 4, 3. Well, that's still not the standard that I need up here. I just need to flip my 3 and 4 to get to that spot. So if I'm looking at this, then I flipped things 1 time there. I flipped things 2 times there. An even number of flips to get from what you have to the standard means that you have R stereochemistry, because the standard that I gave you is R stereochemistry. And then if I would have used an odd number flips, like 1 or 3 flips, then I would have had S stereochemistry. So that's really how it is every time. It's kind of just the same as the examples I did in class. So hopefully just seeing it again kind of helped. If you are having more questions about something specifically with that, let me know. But, that's basically how you do it. Sorry I didn't understand you at first. That's too tiny. Does the dashed line always go to the left and the solid go to the right? Because I think that's all I was doing differently. I don't know what you mean by the dashed line always go to the left and the solid go to the right. Are you talking about when I just drew it from this to that? There's multiple ways you could have done that. There's a bunch of different ways you could do that. If you don't have a good concept, so another way you could have put the hydrogen on top and the NH2 down and the bromine on the right and the methyl on the left. And it would have been, you would have still had to do the same thing and you still would have gotten our stereochemistry. So it really just kind of depends on how you like to view it and flip it. And if you like doing that in your mind, you can, if you're good at doing it. And if not, you need to use a model kit. Yeah, it's much easier if you visualize with a model kit. Configurational diastereomers. So that would be any diastereomer is a configurational isomer. Diastereomers are a configurational isomer. They're kind of like saying enantiomers are chiral. It's kind of double dipping on terms. Configurational isomers are all stereoisomers. So, how do I want to rephrase that? So, configurational isomers and stereoisomers are the same word. Diastereomers are a type of configurational isomer, and enantiomers are another type of configurational isomer. So, you can just kind of mix the words configurational isomer with stereoisomer. And that's different than constitutional isomer, which is what we did on the last exam. And then there's conformational isomers, which are chair flips or staggered versus eclipsed, basically rotational isomers. They're also sometimes called rotamers. I hope that answered your question. I'll be optimistic that that answered your question. I'm sad that it's on my long lab day, so I'm pretty mentally special right now. So I'm trying. You're welcome. I guess that helped. Good. Fantastic. Cyclohexane to a chair conformation. Yeah, so there are different ways of drawing cyclohexanes. So here's one way, right? Just like a standard cyclohexane. I'm going to put on like a disubstituted so we can get some sort of something interesting. So if you want to imply stereochemistry with these, Oh, Ariel, I see your question. If you're curious as to why that's 3 iodo instead of 1 iodo, it's because I messed up the numbering. It should be 1 iodo. So, okay. So if I have, let's just think of, let's do that one as an iodine, and this one here as a fluorine, to make them just kind of easy to draw out. So if I'm showing this molecule with the groups pointing out at you, that means they're pointing up, okay? If I were to look at this molecule drawn, let's see. There's another way of drawing these, and it's called a Haworth projection. And you see these a lot in biology books, where you're looking at it, you're kind of looking at it like if you were looking at it head on. And the fluorine would be pointing up, and the iodine would be pointing up. Okay, so that's another way of just showing them pointing up. We can also show it using chair conformations. Okay, so if I draw 2 chairs here, okay, I can number these kind of however you want. If you want to start with I'll start with iodine and just kind of go around. Actually, let's do it the way we would number it for naming. So 1, 2, 3, 4, 5, 6. Yeah, I'll do it that way. So I'll just put number 1 there. I am really just guessing. I could have put it at any point along here. Sorry. What's important is if I go kind of around there counterclockwise, I should go around there counterclockwise too. So that'll help you kind of keep it consistent up there. So, okay, I have at carbon 1, another color here. At carbon 1, I have an iodine in the up position. Well, at the carbon 1 that I picked here, the up position is the axial position. Okay. If I go over to carbon 3, the fluorine is in the up position. And at the carbon on this one here, it's in the up position. Now notice when I have flipped this, right? Remember that when you flip a chair conformation, you go from everything that was equatorial is now axial and vice versa. So now the iodine on carbon 1 is still in the up position, but now it's equatorial instead of axial. The fluorine on carbon 3 is still up, but in the equatorial versus the axial position, right? So that's just kind of how you translate those from one to the other. You know, if you wanted to draw these as a Newman projection, you could do that. There's a lot of different ways you could go about drawing these, but that tends to be how I do it. So hopefully that makes sense. A common mistake that I've seen, and this typically happens in people who haven't studied enough, is that they will start putting bold lines and dashed lines with chair conformations, which we don't do. Because the chair conformation itself is already showing you the direction that something's going. You don't have to say whether it's going up or down. It's already shown. So don't do that. Ariel, I don't know if me giving you that answer really quick worked or not. Rachel, can you confirm with me that what I just said made sense? 3 iodo, which really should have been number 1. 1, 2 amine. And I've got a hydrogen there. So, just put it there. So the way I do these, Ariel, is I kind of draw the molecule first without any stereochemistry, and then I add it in. That's easiest for me. So if I need it in the R position, then let's see. This would be my highest priority group, second highest priority, third, 4th. So kind of the way that I have it is fine, kind of going in that direction. So there's a couple different ways you could show that. Have iodine there. I can put my NH2 with my bold line there and a hydrogen. Alternatively, I could have done it like this, where I have my NH2 there and a bold line and a hydrogen. You could have had the iodine coming out. Yeah, I mean, there were a couple of different ways you could draw that, but let me know if that doesn't make sense. What part is part 5? Caitlin, what is part 5? Okay, I'm not looking at the old exam, so hold on a second. So just talking about the isomerism question, I guess is what you're talking about. I mean, you basically just need to be really, really comfortable with those words. So for example, at the bottom one, it's methanol and it's mirror image. Well, you should be able to look at methanol and tell right away, even without writing it out, that it's achiral. So its mirror image is the same molecule. It doesn't have any enantiomers or anything because it's achiral. So that one should be very, very fast. Propan 2-ol and propan 1-ol, well, those are constitutional isomers. They don't have the same structure. They don't have the same connectivity, right? We learned those on the last exam. So that should be very, very fast. A meso compound, by definition, is its own molecule, and it doesn't have, it's achiral because of internal symmetry. So that one should be easy as well. The 1,3 disubstituted in cis and trans forms, the 1,3 disubstituted cyclohexane doesn't matter. Cis and trans are diastereomers. So there's key words there, and you need to know what those mean. Okay. An asymmetric molecule and its mirror image with 2 chiral carbons, if it's its mirror image, then it's got to be an enantiomer. Okay, so that's just making sure you're really, really familiar with those terms that we've been learning. And hopefully that makes sense. Damn it, Dennis. Glucose and the 1,3 interactions. Are you serious? Are you sitting there with Stacy and Richard? I'll answer if you're serious. Guys, Dennis is in my biochemistry class. They said they were coming in to crash the YouTube review session. It is relevant to what we've been doing, though. Plus Sally. Guys are ridiculous. Yeah, they're going to look exactly the same as when I put it on the board, though. They're not going to look any different. So, wow, that's an ugly glucose. Let me try that again. So, organic class. This is what glucose looks like. And it has various stereochemistry there. This is another one of those Hayworth projections like I was just talking about. We use them a lot in biochemistry. So that adopts chair conformations, right? So if I put this into a chair conformation, let's put the oxygen, that's ugly. Let's put it so the oxygen is right there. So it kind of looks like what we have there. The one here is the one that can be varied. So in one form of glucose, it points up. In one form of glucose, it points down. So I'll put those in different colors. But the rest of them, so like this one here is pointing down. So here it's pointing down. That one's pointing up. So here it's pointing up. Pointing down. Pointing up. Right? Then, oh goodness, I need to make that bigger. What have I done? I've messed up my, let me see this. Oh, shoot. Guys, give me a second. I have like made the size of my screen too small or something, and now, now I'm running out of room. Okay. So now I can flip the chair. So now this part that was down is now up. That one that's up is now down, right? And the one that was the oxygen is right there still. Okay. So now, different color. The one next to it still kind of has two options. The one next to the oxygen, sorry. The one that's pointing up and the one that's pointing down. I realize there's actually only one there, but so then that one there's pointing down. This one there is pointing up. That one there, whoa, what did I do? That one there is pointing down. And that one there is pointing up. So those are the two chair conformations. Well, technically there's four. So two of them would have the OHs there, and the other two would have the OHs there. And so then for 1,3-diaxial interactions, we don't have to think about anything on that oxygen there because there's no hydrogens on it. So there's one there, 2, 3, 4. So the beta has 4, and then let me do yellow. When you look at the one here, it also has this one, so 5 and 6. So when your OH is in that downward position, meaning alpha glucose, it has 2 more 1,3-diaxial interactions, making it less stable. Ariel, I actually just gave you that exact example, believe it or not, with glucose. So just whichever has fewer 1,3-diaxial interactions. In your book, there's actually a table that has actual like kilojoule energy values to talk about how much energy you kind of add to the system by having certain 1,3-diaxial interactions. I don't ask you guys to do that. I go strictly off the total number, but like if you had 4 and 4, they might not all be equivalent depending on what those 4 groups are, and you'd have to actually physically calculate those with a calculator. Nope. You're welcome, Dennis. I hope that answered your question. And actually, carboxylic acids aren't numbered, as are not aldehydes, because they are always, by definition, at carbon 1. So you can't have a carboxylic acid in the middle of a molecule, right? So if it's part of the parent chain, you know, it's going to be on the outside. So like, let's say, okay, maybe I have one here. Well, that's fine, but now this is my parent chain and I have a dioic acid. It's still considered at the end. Yeah. Now, it gets into a little bit more complicated situation if you have something with an aldehyde and a carboxylic acid on it, but we haven't learned how to do that yet, so just don't do that yet. You're welcome. You're welcome too, Ariel. I've got Twinkie Cam right now. He's being my computer table. Oh, absolutely. No problem, Caitlin. Do you guys have any more questions? I've got at least, I've got 10 minutes scheduled in my imaginary watch. I think it's at least slightly more comforting having a time for some last minute questions, you know, right before an exam if we can. I mean, it's in, you know, about 12 hours from now. Well, 14, but yeah. Here, let me give you one more and you guys can answer it. You guys have done a good job asking questions instead of me just answering them, but here, since we had some questions on this one. How do I do that? Let's do that as a fluorine. And a methyl group. All right. So first things first, draw 2 chair conformations. And if we want to be able to compare results, which would be kind of nice, and on an exam, if you have, like, if there were 5 different ways of doing something, I mean, it doesn't matter if it's not how I have it on my key. If it's right, it's right. But just for the sake of us doing this tonight, let's number it that way. And on my chair conformations, whoa, these are so much harder to do on a computer screen than on the board. So let's do this one there as number 1. So go ahead and do that one. And then here in a second, I'll give you an answer. Oh my gosh. Zelly, are you guys still online? You sent me some emails and I cannot figure out what am I looking at. It, like, Senate rotated in weird ways. Jasmine, I don't know what the yes means. Yes! Oh, yeah, Jasmine. I was talking about Zelly and the other biochem students because they just sent me a desperately worded email. So I was hoping they're still on so I can answer them when we're done with this problem. But thank you for letting me know you're still here also. I do appreciate it. Okay, so fluorine, as shown here, is in the down position, right? So if I'm showing it on this one over here, it's in the down position. And if I'm showing it over here, it's still in the down position. That hasn't changed, right? If I have the methyl here at carbon 4, and it's in the wedge lines, which means it's pointing out at you, meaning it's pointing up. So that one. And then if we have it there, still pointing up, that didn't change. I asked which one was more stable, what would you say? The one on the left or the right? Here. Number 1 or number 2? And that one should be easy to figure out which one's more stable. Pardon me. Okay. Am I saying anything? The lines needing to be parallel with one bond away. Well, maybe I don't understand what you're saying, Rachel, but my bonds are parallel with, like, those are all parallel to each other. And so you're still looking up, down. So if you were saying number 1 is the most stable because it has fewer 1,3 diaxial interactions, you were correct. Well, okay, so Rachel, I think I see what you're talking about. I think I might know what you're talking about. What have I done? Okay. You might just draw ugly chair conformations, in which case I can still figure it out as long as you know which ones, you're looking at. So what that probably means is that you were drawing chair conformations that looked more like this, where the lines were more like parallel with pieces of paper, like the lines in the paper, in which case you're still drawing it, like you should still be drawing it like with those, right? Okay. But you still have the equatorial and the axial. If you're questioning whether or not your equatorial is up or down, look at the axial one. The axial one should be really, really easy to find, right? So remember, the axials go, like starting at the one that's pointing up, the axial goes up, down, up, down, up, down, right? So every other carbon has one going down, up, down, down. Where am I missing? Up. Okay. So you might end up with some that are kind of straight looking like that, like this one here, if you have it parallel with that one because you drew it that way. I mean, I'm like that. Just if you can make sure that you know which ones are axial, then you can figure out if you're equatorial or technically pointing up or down. And I'm fine with that. I hope that makes sense. Okay. We might have, okay. Fantastic. How would we convert one of these to a Newman projection if we were looking down, say, that if I have my eyeball there and my eyeball there? Martha, if I ask you to show all of them, show all of them. But if I don't ask you, you don't have to show them all. And if for some reason I counted off and I didn't ask for it, yell at me and I'll give you the points back because, yeah, I should have known better and asked. I try not to make the assumption that you can read my mind. I'm not always successful on that, but I do try. It's funny, I hardly used Kim Sketch at all today, didn't I? I usually use it a lot more. I said one was more stable, Aaron. That's right. Because it had 0, 1, 3 diaxial interactions, whereas the other one had, what did it have? 4? I think it had 4. I didn't count them out. So if I said, hey, draw a Newman projection of this. Remember, Newman projections are kind of like chair projections. You can show either flip. Okay, you can show either conformation. So the easiest way to go about doing that is to draw just some basic kind of outlines of what 2 chair conformations look like. So there's one. And then when you flip it, oh man, hold on a second. Here we go. Okay. So one chair form would look like that one. In the other chair form, instead of having the Y's in the front, you have the Y's in the back, right? And then instead of the upside down Y's being in the back, you have them in the front, okay? So that means that there, the one in the front, is carbon 4. And this one there is that one there, okay? So carbon 1, the one that's behind there, would be this one there and this one there. And that's the one that has a fluorine on it, and the fluorine is pointing in the down position. So notice there's 2 spots on that back carbon. One's pointing up, and you can tell it's in the axial position, and the other one's pointing down. So we need the one that's pointing down, right? Let's go to the one on the right. Still have one in the down position, one in the up position. Again, when you flip a chair, they don't change it whether they're up and down. They stay down. They change equatorial or axial. So here I have one in the equatorial position because it's pointing out at the sides. And this one I have it in the axial position because it's pointing straight down, right? And the one there on carbon 4, the methyl group, is pointing up. So it's pointing up, right? So that's kind of how you do these. And then everything else gets hydrogens on it. Presuming there's nothing else on it. In this case, there's not. And again, I won't give you anything that you need to put at those positions because you wouldn't use a Newman projection in that context. Like that wouldn't really be a normal use of a Newman projection. Okay. Other questions? I have time for one more and then I'll answer these questions for biochem if they're floating around. Did I leave off a hydrogen? I did, look at that. Oh, Dr. Man, you're naughty. Bad me. I'm so happy that you think so, Jasmine. It means a lot to get positive feedback on this kind of weird little YouTube live streaming thing that I do. They're really cringy for me to watch, so I never rewatch my old videos. Like, I'm afraid, like, you'll see me like picking my nose or something. Or my dog is acting weird, or... Look at that. I'm just so naughty. Bad Dr. Man. Okay, well, I'm going to stop answering organic questions right now. And I'm going to answer a few of the biochemistry questions, and I'm not sure if they are online or not. To draw both the side up and the upside down Y on the Newman projections. Well, Hannah, that just depends on the question I ask you. You need to know how to do both. If I ask you to do both, then do both. If I just ask you to do one, just do one. Okay? I will see you guys in the morning. Let me figure out what these questions were that Zelly and the other kids were asking. Okay, so I really wish I could rotate this. Can I open that with? Okay, so let me do it this way. Snipping tool. Snipping tool. No. Can I not rotate in here? Yes, I can. Okay, good. Left 90 degrees. Oh, fantastic. Okay. Zelly, I have this how-do question. As in, how do? The cellular concentration for malate is 0.3 millimolars and fumarate is 0.1 millimolar. What is the free energy for the reaction? You have this equation. Let me figure out what time this is. Does this not tell me? Okay. Like an hour and 10 minutes. Okay. So, I see the problem here. If you notice, you have to write constant here. You made negative. It should be positive. The only reason you're used to seeing it negative is because when you're solving delta G naught prime, that's equal to the negative RT ln of KEQ. And that's just when you solve when delta G prime is at equilibrium, it's equal to 0. So when you solve for that, this is the equation that you get. But that should be a positive 1.987 times 10 to the negative third. That will give you a drastically different answer. So check that one and make sure that that makes sense. And then, wow, I actually had a pumpkin on that exam. That is amazing. And then number 1, the standard state free energy. Let me do this again. There's got to be an easier way to do this. But if there is, I don't know it right now. Okay. If the standard state free energy for the forward reaction is negative 2.4 kcal per mole, what is the KEQ for the reaction? The KEQ is 57.4. I agree with that. I don't know if you just wanted me to check your work on this or if you had a specific question about it, but this answer is correct. Check. That is supposed to be a check. Let me try that. Finger. There we go. What is the ratio of P over R if the true free energy of the system measures negative 3.2? So negative 3.2 equals, no. Okay. So the true free energy is not the standard state free energy, right? So here you are looking at delta G prime is what you're trying to solve for. So you need to use the delta G naught prime plus RT ln of Q, or P over R. So you just had the wrong form of that. What percent of the reaction in problem 2 above is the reactants? Thanks. So if you're looking, you found what percent is product, it looks like. So if you're looking for the reactants, it should be, oh wait, no, I see. You got it, yeah. That's right, you got it. I was just not looking at your math right. Okay. And then next side view. Difference between enthalpy and entropy. Enthalpy is the heat energy. Entropy is the disorder. Exothermic versus exergonic. Heat favoring, or heat leaving the system, tending towards spontaneity. Yeah, or just negative free energy is another way of saying that. Kcat of 3 is the turnover number, so the number of reactions per second for an enzyme at Vmax, so at maximum velocity or complete saturation. So, so it basically is just saying that, that's how many reactions you can have per second. I mean, like 3 reactions per second when you're saturated. So, yeah, you answered that just fine. And then it achieves half Vmax at substrate equal 0.001. So when we're saying that the Vmax, okay, let me show this one. Oh, that got ugly. Sorry. What percent of Vmax is the velocity at substrate over Km equals 1 over 10? Oh, I did the wrong one. I just highlighted the wrong one. I'm sorry. Let me try that again. So we actually did a couple like this in class. So also double check your notes. must have been feeling incredibly festive when I did this one. Okay, so 1/2 Vmax at substrate equals 0.001. So essentially, what are we asking? What information is that going to be? So if you're doing your 1/2 Vmax, your substrate at 0.001, okay. Vmax times the substrate concentration. Whoa. And the Km in this case is 0.001 because that's the concentration at 1/2 Vmax, right? So let's see. Your velocity would be 0.002 over 0.003 molar. Times Vmax. So 2/3 Vmax. So you could either report that in terms of Vmax as a fraction, or you could do it as a percent, so 66% of Vmax. Okay, and then what percent of Vmax is the velocity at? That's kind of the same sort of thing. So you can solve for your Km, and again, get everything in terms of your I just lost my train of thought. I'm so sorry. I think my brain might be fried after all today. But so that would be 1/11. So substrate over Km is 1/10. Is that right? So 10 times the substrate's equal to the Km. So that would be 1/11. Yeah, so 1/11 of the Vmax. So 1 divided by 11 is whatever percent that is. What is that, like 9%? I think is what that comes out to. Okay. And then a good inhibitor is so an allosteric inhibitor can be different. I mean, it can be either. Yeah. So you can get mixed inhibition. I'm not sure why you say it sounds like uncompetitive. I mean, you would just needed non-competitive and then to draw that, which you did. So I'm not sure what question you have on that one. I'm sorry, Zoe. And then 100 millimoles per minute, micromoles per minute per milligram. Yeah. Number 11 looks good too. And your histidine is... double check your histidine. You have positive charges on your amines, but you only put 2 hydrogens on them. So a positive... Oh my god, my neck. A positively charged amine should have 3 hydrogens on it there, or at least have 4 different covalent bonds. And then... Arginine looks good. Okay, yeah, so the rest of your stuff looks fine. So, okay. I will stop for tonight. I don't know if you guys are with me still. It says 2 people are still watching. I don't know if they're biochem people or organic people, but anyway, I will see you guys in the morning. I'm getting pretty tired today, so I'll probably actually go to bed early. But I'll be happy to answer any emails as I get them. So, you know, feel free to email me, and if I'm awake, I'll still answer them. Okay, so I'll talk to you guys tomorrow. Happy studying, and good night.